Next, next speaker will be Super Wim. He always called nickname is Super Wim. The Wim Simon, he Belgium national, but study and working in Netherlands for some time. So here is his biography, 25 years. You can see on the video. Is it ready? Two, yeah.
First time I came to Thailand was back in 1997. Actually, the research we did involved all Southeast Asia, and my boss back then, he had my ambition to expand my research beyond the project we worked in before, and that included to do more work also in Thailand. More or less on the topic I'm working on, and also on using satellites to study the Earth, which can be sea level rise, earthquake area. Of course, if the climate change or sea level rise is going to make problem for the beaches, for example, or some cities like Bangkok, then that will create stress for the people living there. So in some way, I hope that our work, or also my colleagues, will contribute to preserve the smile. So the Thai people can smile also when they walk onto the beach, and keep on doing that for hopefully many generations to come. Not only for my own interest, but also for the benefit of other people. This kind of work I've been doing. So when I came to Thailand, a lot of people are always nice. They ask you how you're doing. It seems genuine. It doesn't seem that they're just polite to you to expect something back from you. And that I really appreciate a lot. Thailand, the people seem to be more nice, always smiling, and very respectful also. So I really enjoyed that. Yeah, anywhere I go, I think Thai people always are friendly. So yeah, so it feels to me relaxed to be at home. Sawadee-krap, ผมชื่อวิม ผมเป็นคนไทย ขอโทษนะครับ ผมเป็นคนเบลเยียม ทำงานที่เนเธอร์แลนด์ ที่ Delft University of Technology. To participate, and actually we'll be on I think on Thai PBS soon, a longer one. But it's more about my life experience doing the work here, which has been like about 25 years. But you see my motivation, because I always enjoy to come here. And of course the research is important, but if the environment, the people are nice, that keeps me going for already quite some time. So it's my pleasure to, if the pointer. Oh. Yeah, but you already skipped to the first slide. So I still had my title. It doesn't go back. Can you push my title sheet please back up? Huh. Oh, okay, thank you. So today, actually, I'm doing quite some time doing the work in Thailand, but my participation in this project, as Professor Femke already mentioned, is mostly on GNSS. Nowadays we talk about GNSS, the Global Navigation Satellite System, but it's actually better known as GPS, which was the first system from the Americans. And nowadays we also have other systems from Europe. We have the Galileo, we have Baidu from China, and there's a couple more of them. But most of the work, what I'm showing you today, is actually all using GPS, because that was available already for research, the data and the satellite system, since 1994. Doing this, I've been working with actually my colleague, which is going to do the next talk, Mark Naye. So we're quite a good team because we need each other data, as already Professor Wemke explained. Mark looking more at satellite altimetry. So he's looking at the absolute sea level rise, also looking at tide gauges, which are also sea level rise, but relatively. So if the tide gauge is measuring the sea, it can be moving up or either down, which is creating more or less sea level change. So that's why we call it relative sea level rise. And quite new topic I'm working on, I'm also showing you, is using GNSS as a tide gauge. For that, also I'm working with one of new colleague who is an expert on that, also from the UK. And of course, Captain Samart, which all the years has actually helped me, also because we have to maintain the stations, keep them working. You saw in the movie the example for Phuket, because the movie crew followed me there, but we also have stations in Bangkok, which we keep on running for many years. Because in this study, we have to know for over a long period of time what relative sea level rise, but in my case also vertical land motion is. So we need long data from the same locations, many locations, but the same over a long period of time. Yeah, and right now also Captain Samart is at this new university, which I'm not going to try to pronounce. After he retired from the Royal Thai Naval Academy, he's now also still active at the Navimindrai University in Bangkok. Okay, the contents of my talk today. I'll talk very briefly about the concept, but you'll hear more about that. Professor Wemke already talking about that. The mean sea level projection is not at all what I'm going to talk about, but we got a nice question about before. But we try to add local data to that. Then I'm going to... Okay. Then I'll talk to you very briefly about the space geodetic research activities in Thailand, what kind of techniques we have been using. Also now, the use of GNSS in relative sea level change studies. So that means we can not only use GNSS to estimate position with millimeter accuracy, but at the same time, if we put the GNSS station at the sea or near the sea, we can also use it as a tide gauge, or we can compare with that the tide gauge shows. Therefore, it's actually good to put GNSS station together with a tide gauge, because then you have two independent ways to measure the relative sea level rise. So vertical land motion, that's mostly what I'm talking to you about today. Of course, we have horizontal. We see a lot of changes from the land after the big earthquake, which are still going on, but they are less important for this long-term vertical land motion, which in the case of Bangkok mostly are the result from land subsidence. Then the reflections, as I mentioned to you, I will talk to you briefly about a bit about the tectonics, but not much, because I need to, it has some role, even play some role in Bangkok, only be it maybe for a limited period of years. And then the most important thing is the, what is important is what we try to do for Bangkok, we already did for Phuket. And that was actually our study case, to see if what we want to do is measure relative sea level rise in different ways. So there are 3 ways, independent techniques we can do, as you see. One involves satellite altimetry, which Mark talks about. That's absolute. If we want to make it relatively, we have to know what the land is doing along the coast. Then we use vertical land motion from GNSS. The tide gauge, the traditional one, is showing you directly the relative sea level rise. And then now, as an addition, we also have GNSS reflection, which also works as a tide gauge. So that's very nice. You have 3 different techniques, which you can all employ at the same location, because then we can validate. So if we have one result from data, that might not mean it's the truth, although most of the time, if you do it properly, it should be correct. But now we have more ways to validate this, so that's quite nice. And of course, I'll show you at the end the updated results from the stations we have been monitoring in Bangkok and what they are doing. Of course, some conclusions. Okay, relative sea level rise. I also have this nice plot when I flew. Actually, this picture I took myself flying into Bangkok. And then you see, of course, Bangkok, and you see here, of course, the coastline. And then actually the temple, which also Femke mentioned, is actually here. So it's not, it's more like in the greater Bangkok region. But you can clearly see that this temple is nowadays inside the sea. But we did an excursion there. And we'll do it actually again tomorrow with some of you. And then you can see that the temple actually was clearly located inland in the 60s, I think, late 60s. And then we move on to the 70s. And to present, you see that the sea is actually gaining, or overrunning the land. And nowadays, the temple is here. Because the monks want to preserve the temple, this is very nice. What you can clearly see here what the impact is of relative sea level rise, where the land is going down and then the sea is going up. The sea we don't have control over, and it's mostly related to global climate changes, and there are some regional changes. But of course, the land subsidence, that's the one you can control. You cannot control it if it's controlled or the result of tectonics, which also happens, but those are smaller signals and they don't make this huge impact. Of course, groundwater extraction, that's the main cause for land subsidence. We see in many areas where we have sediment layer with aquifers, and there is groundwater, which is of course normal to use groundwater, but if you pump too much in a short time, then of course the land on top will sink. That's why the sinking Bangkok is quite nice to illustrate this. So another way actually to look at this, and actually we did some studies in the past. This is already a study more than 13 years ago. And Mark will talk to you about that, is to look at absolute sea level rise. Then we also, of course, interested in this coastal region and what it's doing. And for that, talking about the traditional way of measuring that, that was typically done using tide gauges. So here you see two tide gauges from Thai authority. So we have the Pom Prashumt and the Bangkok Bar, just to illustrate you. Then if we look at them, because they go back very long, because tide gauges, they don't use satellites. Everything which with satellites is actually from the early 90s. We start to be able to use that data to look at. So that's just a quite short period. But the tide gauges already are around much longer. Some of them even go back more than 100 years in countries. While here you see actually what the tide gauge is measuring. There's a couple of them. So if it's like this straight, that means it's quite okay. It means that the sea is not going up a lot with respect to the land. However, if you see this sharp increase, which you see two of them here, they see an increase in sea level at a rate of, I estimated roughly from the graphic back then when we looked at it, which starts around the 1960s. And then you see this huge increase by 1 to 1.5 centimeter per year. That, of course, is much higher than the sea level rise, which was back in the 60s, not that big topic, but you saw very clearly that, the coast saw the sea increasing much higher. Why? Of course, because the tide gauges were subsiding. And never mind those two. These are two adjustments in the datum, so the vertical reference height. So they don't mean something changed here. Just focus on this one. So this is quite something you can see. And also Thai people have studied this. And then when they look at the coastal change, it's a paper of 2010, they can clearly see, which is shown in the pictures, that the coastline has retreated in this part, especially this part of southwest of Bangkok. But also near Samut Prakan, there are, although you don't see it here, there are similar cases where, if you build a dike, you can stop the water. If you don't do that and you have mangrove forest, the water will penetrate the mangrove forest, and coastal erosion and storm surges, and then you will lose coastal line. The absolute sea level rise, actually, this was an old estimate back then. Mark will tell you more about that. Now, talking about this mean sea level projections, I don't want to mention anything about that more in detail because Dr. Eme will talk about that later on. But it's important is our contribution or my contribution in this. And one of them is that to replace, these are actually suggestions from this panel, to replace the vertical light motion command by regional estimates and compare sea level models with regional measurements from satellites. So that's exactly what we're also doing in this project to do that. Now to look at those, I think those two ones, the questions to Femke, Dr. Eme is the expert on that, but I think this was a moderate one, and it depends if we can reduce our CO2 emissions by a certain goal, and if we don't do that, then it will become even worse. So that's, this is actually the best case scenario I think about in the worst case, but more on that later on. Now, research activities from my side, well, the one people working with me here in Thailand, is that we are operating actually nowadays 4 of our own stations. I mean, there's many more stations in Thailand, but we actually try to keep the same station at the location operating for a long time, because then it becomes valuable. If you just put up a GNSS station for 2-3 years, and then your project finish, and then you stop the station, that's nice, but that's not gonna, especially for the vertical, is not gonna give you useful data. So what we have tried is to operate, besides we also share data with other government agencies, like for example, the Royal Thai Survey Department. We try to have these stations operational. 2 of them are located in Phuket. That's what you saw in the video. We saw 2 of them there. They are close to or at tide gauges, so we can compare for the relative sea level rise. And then we have the 2 stations here, which I talk a bit, and then the one is operational since 2005. And then there was an older stations from another project, which was operational until 2006, and we try to combine that data so we have a longer period of time. Of course, we have been working with universities in the past, government agencies. I already mentioned to you Royal Thai Survey Department, Chulalongkorn University. We also been working in the past, so that's nice. From our side, of course, we're also interested in this effect from this big earthquake, both horizontally, because the geophysicists, they want to use that to understand better this mega earthquake cycle. But for today, I think it's more important to see how we can get long time series, which is a collection of positions with like this millimeter accuracy over a long period of time, and see how they change. And now we focus on the vertical direction. So the vertical direction, of course, is the component which will measure the land subsidence, and also we can use that to combine it, as Mark will also show, to use satellite altimetry to get the relative sea level rise estimate. And also the GNSS reflections are quite nice technique. Now this figure you saw from already from Femke, but what I want to show you here is just what my part is, and that's 2 things. That's the vertical land motion, which is measured by the GNSS station, and then now quite more recent, we also use the GNSS signal should actually arrive in the center of the antenna to get the best position, but some of them do not. We call it multipath, and if the station is nearby the sea, some of the signals will reflect on the sea, and then they will enter the antenna. Normally, we don't want this data for position because it's noisy data, but some other people, I think the last 10 years, they designed this technique, which allows us to actually measure the sea level height by looking at those reflections. So that gives us an additional technique. And then here you see actually this, it's not a complicated formula, but relative sea level rise, you can measure directly with the tide gauge, or you can look at satellite altimetry. Mark will talk to you about that. Subtract the vertical land motion at the location, where you also have satellite altimetry, so it's a coastal region, and then you can get. But you can also nowadays use directly GNSS, the reflections. So you see we have 3 options to study. We can use the same, as I mentioned, in one location, or we can use different, depending on what data we have available along the coastal area. So I focus more, of course, on this part. Vertical land motion. What is vertical land motion? I think it's quite makes sense what it is, but it's actually, you can actually call it absolute. This is something which it is important to realize, is that we can measure land motion, vertical land motion, either in absolute form or relative. The INSAR actually is always relative. That means the INSAR is a radar image with pixels, and it's combined. I think you later on you'll hear from Dr. Anapa, also from Dr. Milan, how it works a bit more. But it's always relative in the radar image. So that means if the whole area which the radar image is covering is going down also by 1 centimeter per year, you will not see that in the INSAR image. Because the INSAR image is only showing relatively with respect to the highest or the lowest vertical land deformation, and you can put your scale somewhere in between. So that's actually, it's useful to still have GNSS, even if it's a few points, because then you can calibrate the INSAR. And if we see, for example, there is 3 millimeter per year everywhere on the Bangkok subsidence, then we can still add this 3 millimeter per year to these maps if we look about vertical land deformation. What can make vertical land motion? Well, crustal deformation can do it. So that's actually the tectonic plate. It can either be deformed upwards or downwards. That this one, of course, for Bangkok, although the first one also applies to Bangkok, but it's not a very big signal, but it's still nice. We still observe it, and at least at some point it makes the subsidence rates a bit different. But then, of course, the most important one is human-induced, caused by humans as a result of groundwater attraction. Of course, we have seasonal changes. I think Mark will talk about a little bit more about that, because if there's more water coming, then you get some different loading, and the vertical land motion might change. But these are yearly signals normally, and they don't really make a big problem. It's of course the trend over a long period of time, which is for predicting also important, is the most important one. Of course, you have to know the seasonal change, because it can be different between the seasons, and the difference in the Gulf of Thailand of the water can be quite high. Of course, you will still use that as a margin. If you would have a dike, you would have to know that, for example, there is 25 centimeter difference from the mean sea level height in the Gulf of Thailand through the year because of the seasonal variation. Then you have to use those 30 centimeter if you build a wall to make sure, apart from a safety factor, you do that. Techniques we're using, I already mentioned to you, and a bit about the data we have available. So for Thailand, we have 1994 to present. That applies also a bit more to Bangkok, but most of the daily data from continuous station is end of the 90s, it starts. Satellite altimetry, Mark will tell you about that. That's also since the 90s we have. And then, of course, this one, INSAR, which we talked about later. Now, just to talk to you about a little bit is how it works. GPS stations, I think you know it, you have it on your phone, although your phone is like meter accuracy. If we process the data later on, we use accurate orbit from the satellites, and then we can actually get down. And we use also 2 frequencies. We measure not only the code signal, this is one which your phone is using, but that you only get meter accuracy. Your phone can give you at best 3 meter. If we use the 2 double frequencies and the phase of the signal, we can get this millimeter, but we have to use 24-hour data and average and do some scientific modeling around so we can get that. What you see here is actually one of the stations, RTSD, the base station, which we installed shortly after the 2005 earthquake in Bangkok at the survey school of the Royal Thai Survey Department. And this station we have kept operational all those years, which is almost 20 years by now. And what you see here, you will see later in detail, is the vertical land motion or the vertical motion of that station. And actually, I think the station also is one of the longest running core stations in Thailand. So it's been working daily. Sometimes we had a problem, equipment broke, but we always try to fix it within a couple of weeks or as fast as we can, and keep also the station updated with the latest equipment. A little bit, very briefly about tide gauge, but I don't want to go into detail. Mark will show you a little bit about that, but what's our contribution from GNSS side? What I'm working with is that if you put GNSS station nearby the tide gauge, then you can also measure, of course, the vertical land motion direct of the tide gauge. Actually, this is the one at the Naval Dockyard. The tide gauge is here in the back, and we put 2011. We have put here the GNSS, so we can now also measure the vertical land motion. And we also plan to combine this with the data of the tide gauge. Now we can see from that. And of course, in the river, actually, we're going to try to do the reflection. Although it's not so easy to do reflection in a river, because yeah, there is some areas where there's boats passing by. They might block the signal reflecting on the water, but we're still going to try to do it. Although a dedicated station might do a better job. Then we put the antenna maybe on the corner of the river, so it has a free view also of the river. Back then, we mostly focus on the vertical land motion. Okay. Reflections, what I talked to you about. So this is what my favorite, new hobby in the past years is using a traditional station. This is a station we have at Phuket. And then we are using the reflections from the GPS signal. So this is the one we really need. The direct signal is perfect for position, but the multipath or reflected signal we can make use of to measure the sea level height. So it's relative sea level height is that actually as a tide gauge also is being measuring. And then you see actually it works quite well. There's actually a simulation you can do. So these are the areas where you can expect the signal from the GNSS satellite to reflect on the sea surface, and then it will enter the antenna as the noisy multipath data, but that's exactly the data you can use. You see that it doesn't come in all directions because it has to do with how the satellites or which constellation you're looking are passing over in the sky. Also here you see there's land and there's a hill here, so probably this kind of data we cannot use because you cannot use the reflection over land, although it might reflect, but that's not showing you the height of the sea. So but altogether it's not too complicated to run the software. If you have a nice area from here to here, actually we can monitor the sea level. So this you see on a monthly basis. Of course, a tide gauge is doing it every hour. Reflection depends on when the satellite is coming over, and also if the weather is very bad, it becomes stormy weather, then sometimes we don't get so good reflections. But we still get enough to get an idea. This is what you see over a month of time, and then you see clearly this tidal signal in there. And you see the same over a year, because you have the monthly tide going up. So so this is the new technique. I'll show you. We're going to try to do this still for Bangkok with some data we have, but we might also for the future install a dedicated station to use this technique also along the coastal area of Bangkok to study. The plate motion, I talked to you a little bit about. This is something we see more in Phuket, although it does, and I think it's something we might want to look in the future, but that's more from scientific interest, that there's also some tectonic part which affected the vertical land motion of Bangkok. But that one is not important or critical at all for this relative sea level rise we're talking about. And that's actually part of this cycle. I don't want to go into detail. Actually, later on we also will provide a link where you can get presentations from today. There are 3 phases in this megathrust earthquake, and it will repeat again. There's interseismic, basically before the earthquake, during the earthquake, after the earthquake. And you have different motions, both in the horizontal and the vertical direction. Just to illustrate you here for Phuket, but I also could have put Bangkok, although it will be a little bit further away. You see an area where these 2 tectonic plates are locked, and the one is actually dragging down the area and compressing it. So some parts of the land will move down, other ones will move up. And then when the earthquake happened, actually the plate can, like an elastic a little bit, it can rebound. So an area will suddenly start to move up while it was going down before, and similarly the other way around, depending how far you are from this megathrust, which is far away in Indonesia. But even in Bangkok, it had an impact on the vertical land motion. Smaller signal, in Phuket was more clearer. Just to that, And then we looked at it. This is a very old result, but this together with Chulalongkorn, that even this vertical change of land motion will have an impact, or could have an impact. This is an older study in the Bangkok area, but you see the total magnitude would be less than 10 centimeter. And also at some point, it's like you pull something apart, you compress it. So the 10 centimeter is actually not a seasonal signal, but the signal maybe on 200 years. So it's not a permanent thing to look at. So, but that's a nice thing to see this extra detail. Then when we look at the we look at the study case. Actually, we did the study case because there we had all these different techniques available, and we want to ensure that it works. We publish about that so that when we apply it to Bangkok, we can also show or convince the people, or some people who may be doubtful about that the work we do can be validated even by using different techniques. Mark will tell a little bit more about that. My most important contribution, what you see here is, this is 3 GNSS stations. Actually, this is a point from the Royal Thai Survey Department from an old project, which is still being measured at Promthep Cape. This is very nice because we have data from 1994, and still yearly, Royal Thai Survey Department is measuring this point as part of this TAICA network. And then we have our own station we installed back in 2017. And then we put one more station at the end of 2019 at the tide gauge of the HDRTN. So the Hydrographical Department, Royal Thai Navy, they have a tide gauge already which has been available for, I think almost 100 years. So we also put our own GPS, or GNSS, sorry about that, on top of that. Okay, this just to see what's involved. So you have to look for a location, bring your equipment, and then, make a construction to put the antenna in the equipment so it can last for, in our case, well, hopefully longer than I retire, which is 15 years, but the station, if you want a good station, you try to keep it running for as long as you can. Until we maybe in the future get this new technology, we can, like in Star Trek, we can just scan a planet in seconds, but I think we're still some distance away from that. So we try to keep this station operational. And then we also try to combine it actually with existing data from other stations to make this time series very long. Okay, this is just to show you what we can come up with then. Now you see that since 1994 till now, we have the position of Phuket. The first two ones, I don't want to go into detail, is the horizontal. What you clearly see is the impact of the earthquake in 2004. And you see before the earthquake, actually, the station was moving nicely in a straight line. After the earthquake, the station is not moving in a straight line. And actually, it's still moving at a different way as before the earthquake, which tells us that even today, we are still in the post-seismic from this big earthquake. 9.2 earthquake is quite big. This different motion can last for decades until it slowly should go back to this more linear one. Now, if you look at the vertical direction, you see actually something different, well, similar, but you don't see a big jump when the earthquake happened, but you do see that before Phuket Island moved up, and afterward Phuket Island starts to sink for a while, but it's already starting to flatten out. So this is actually something we also see in Bangkok, but at a smaller magnitude. And then this is then the VLM, the vertical land motion, which is then like this. Mark can then model it and put a nice yearly signal or semi-yearly signal through it. At the same time, we have tide gauge data available at the same location or very nearby, and satellite altimetry. And then we can do this combination where we can compare if the tide gauge signal is the same as the signal we get from subtracting the vertical light motion from satellite altimetry. Then they both become relative sea level rise. Okay. And actually, this one is the longest one we have. Okay, this one, Mark can tell you more in detail, but our conclusion is that it's not perfect, but it does work. So we have two different ways of comparing computing relative sea level rise, and they give very similar results. There is still some differences, but altogether, I think this is very nice. We can validate in different ways. Now, in the future, we also want to include the reflections, because the reflections from the GNS, they work as a tide gauge. Just to show you that, this is two of our stations in Phuket. What you see here is a tide gauge. So this is daily, the daily mean sea level. So it's average over 1 day over a longer period of time. And then what you see here is actually the reflected signals from the sea captured by the GNSS. And what you see here is that they do exactly work, or they work very well as a tide gauge. So this is a change of the sea and the mean sea level changing on a daily basis over a period of a couple years since 2017. And you see that using this reflection, we can do the same. So we have a different way, or example, if the tide gauge would be broken, but we still have the GNSS, we can still monitor. So for Bangkok, tide gates already exist, but it would be interesting to also maybe put more of this station. Of course, these stations have to be located, they have to see the sea or the river or the mouth of the river, as well as they see the sky to get the satellite data in both ways, direct for positioning and indirect to get the reflections of that. So, and then the second station actually we put there, so we have quite some redundancy in Phuket. Was operational for a shorter period of time, but also here actually we see actually it's actually the same. It's a different scale, but we see again that it can follow the tide gauge data quite well. So this is quite new technique developed, and it's actually not too difficult to master. Of course, you need to have a station available to do that, which is getting these reflected signals from the sea surface. Okay, almost getting there. Yeah, and then if you look at the difference between, if you subtract the tide gauge, you have the tide gauge in green, and then we have this reflections. You can see that they actually overlay quite well. This is not the difference, but these are the different signals. So if for some period you don't have the tide gauge, yeah, you still have the data from the GNSR reflections you can fill in, and you can continue and keep on monitoring. We hope that this technique, but it will require more years, can also give us an estimate on the relative sea level rise over 5 or 10 years, you know, so as we use the tide gauges for. So now, getting close to the end, let's focus to Bangkok. In Bangkok, there are not that many, although nowadays there are more GNSS stations, but there are not stations for already a very long period of time. So if we look at this, there are a couple stations we have available. We have our own station here, or in cooperation with, and one station here. And then you have an IGS station at Chulalongkorn University, and then there was an older station here. This is also a station, I will not see the result yet here, but this is a station from RTSD, which was installed back in 2019. And in the last 2-3 years, I think the data was too short, but now they almost have 5 years operational, so it might be useful also to look at this station. There are a couple more I will show you later, and we're still going to include them. But it's not like with INSAR we have 100 stations available, but at least we have some, and for quite some period of time. Now, if you look at that, you see something similar as you saw for Phuket, but I want to focus on this graphs, and these are the vertical land motion of the stations. And these are the red ones. Actually, this one, ignore this one. It's actually, it will make sense later. But these are the 3 vertical land motions we get. This is actually combined. It's a bit tricky, of course, because the one station is at a different location. For the horizontal deformation, it will not be a big issue. Of course, vertical land motion can be different, as already Professor Femke and Jenny will show you later, depending on the ground walls. However, the question, what is important is to notice here that what we measure is vertical land motion below 20 meters, because all the GNSS stations, they're on buildings or they're on a pier, and all those piers, they use concrete foundations, which are at least, what we know about, we checked that, 10 or general 20 meter deep. So what we measure is only the subsidence below 20 meter. So anything which subsiding above that, from the surface to 20 meter deep, the GNSS will not see, unless you put the GNSS just on the sand, but the INSAR does see it, so that's nice. So in general, the estimates you get here will be lower, because a lot of the subsidence is going on in the shallow layers or the first 20 meter of the sediment layer. So if you look at that, you see actually, it's quite hard to see here, but that we are nowadays for those 3 locations, actually they're quite similar. The rate, although they're different location, is between 2 and 3 millimeter per year. So that's absolute. Huh? So that means, that could mean that the whole area of Bangkok on average is nowadays, or the center of Bangkok where we have the data, is going down by 2-3 millimeter per year. But the upper layer can maybe have 1 to 2-3 centimeter, as you see later. So that one we have to add. Now, if you actually compare if we just have the time series of the Chulalongkorn overlay with RTSD, we see that it's almost the same. But then again, they're not too far apart. They're only 3 kilometers apart. So that means they're probably, we have to verify this, but they might be above the same aquifer. So they see a very similar thing. Now, if we look at the station all the way in the south, in Subut Prakan at the Naval Dockyard, and we overlay that one, it's just an example, because here you see the fit is quite nice. There is something different here. I will mention to that. That's a nice detail. So if we do the same here, that you can see that the Naval Dockyard, or the area which actually is close to the temple, nowadays, at least the pier, which is on 20-meter deep foundation, is actually a little bit less subsiding, but we're still subsiding. You do see actually that there's a change, an increase, and you see that very well here, that before the earthquake, we had higher subsidence rates. Unfortunately, we don't have too much data, but then after the years after the earthquake, it seems like the subsidence magically has been reduced, but now it seems to increase again, and it might go back to these rates. So this is not, for me, it's a nice finding, but it's not too critical. It may have to do with how the sediment tail layer responses when the bedrock, which is tectonic motion is making the bedrock, go down. It seems that somehow it reduces these rates for a while. And to show that a little bit, that it's not just maybe groundwater pumping below that station, I just project the Phuket, and you see in Phuket we had the change in motion start after the earthquake. It starts to go down and it starts to flatten out. And actually in Bangkok, we not see Bangkok itself move down, but we do see the stations, I'll not show you here today, the stations nearby Bangkok, like in Chonburi or in Rayong, which are on bedrock, or more bedrock, we do see also subsidence. But the station in Bangkok, which are on the thick sediment layer, we actually don't see it, but then later on, the subsidence seems to increase again. So it's a nice detail, but it might be interesting also if we look in, for example, subsidence in these years, that we know that for a while there might be a period where the temporal rate has increased. But that's not a big issue, because we are mostly interested in the long-term rates also for predictions, and of course there we can measure that. So I think that's we're going to try. That brings me to my last slide. So for now we have 4 locations. We combined 3 to 4 in Bangkok, and it shows that we have actually land subsidence, and like I mentioned, I have to mention to you below pillar depth. So that's everything which is moving down below 20 meter. That's what the GPS is measuring. The soil from 20 meter down to up might have bigger subsidence rates, up to a couple centimeter. We see that generally in the past, actually we had 5 millimeter. Nowadays for those locations, we only had 3 millimeter per year. Okay, that made me think, yeah, that's good news. And it means that your building is only going down at 3 millimeter per year, but the pavement and the street below might be going down quicker, so you will still have an issue with flooding. So, okay. So that's what also the INSAR will probably show you. I think it is important, and we're still going to do that in the past years, is that we're going to add a couple more GNSS locations. It's not easy to have those stations for a long time operational, but there are a couple candidates, and we might expand a little bit outside of Bangkok, also to the area which is the INSAR data is covering, because the RTSD core network, they start in, I think, the middle of 2019. They almost have 5 years of data. So we're going to look at a couple of their stations. We already sharing some data also for the study we do in Phuket. Another station I already planned to include long time from the National Institute of Meteorology. It's also in Bangkok, and we're going to see. So there's a couple more. And there's more stations at departments of land and town and country city planning. But those stations, in general, they were put up for a couple of years, but then the project finished, or the maintenance, so that we already had a bit look of them. Most of that data might not be suitable because the station are only operational for a time of there is data missing because the station is broken down. We might have a look to see what we can still include. So this one also, we also can contact, or we already contacted before Chulalongkorn University about that. So okay, so just this one, which is a small thing, but still nice, we can see it. Vertical land motion in Thailand has been temporarily altered by this big earthquake. However, I think the future impact of human land subsidence is larger. That's the one which is also a threat for this sinking Bangkok thing. Vertical land motion in the coastal regions, they can provide us with the validation of the tide gauge results, so that's nice, in combination with satellite altimetry. Mark will talk to you about that. Our first GNS reflection, we're really enthusiastic about that. It's all quite new. We had to do it in Phuket because there we have the nice combination of the GNSS station near the sea already available, and the tide gates as well. But there are also suitable locations, I think, around Bangkok, or maybe a bit further away from Bangkok, but we have to check if there are DMR, for example, has 2 tide gauges, one in Rayong. I think one is a little bit the Gulf of Thailand, but there might be more opportunities to do. Maybe we can put an extra station to look at this technique. So that's quite nice. Yeah, and then validation, I think, is quite nice to have more than one technique. So if somebody is critical, even the scientists, but also the policymakers, you can say, yeah, but we have actually measured this in 3 different ways, and they all show the same similar signal. So, okay, that's the final word I want to talk to you today. So thank you for your attention. And maybe for the questions, we can also do later at the conclusion, so we stay on schedule.